care that's affordable and is easy to administer. And the era of integrated computing allows us to offer some new answers to those old questions. What if we moved healthcare out of the hospital? Care that's actually tailored to the things that are going on in your body. There are a tremendous number of other devices and other applications, injectables, ingestibles, that we've looked at. I didn't have time for all of them today, but all based on the fundamental, foundational building block of this industry, which is the silicon transistor. Customized care with your own genomic data is the pinnacle of healthcare. And we first mapped the human genome using an Intel high-performance computer, the Xeon-based computer. That's pretty exciting for us. And as you can imagine, because we like to talk about big data, that is one big data challenge. And I like to share how big of a big data problem. One person's genomic map is a petabyte of data. That's 1,000 terabytes for one person, enough to fill 20 filing cabinets of information. And through the work that we do, the advancements in price performance, Moore's Law, what we do every single day, we've transformed the ability to sequence. And what used to take years in 2000 is now down to 2 weeks, and we're working to get that down to days and hours. But more importantly, a single sequence used to be $70 million. It's now less than $5,000 to do one sequence, and we are en route to make that $1,000, which means personalized genomic sequencing is within our reach. And it's moving faster than the rate of Moore's Law. But let's think about the benefits of that. Why are we excited? Why am I excited about that? Why do we get up every day and say, you know what, working with Intel, working at Intel, it's pretty exciting because we get to change the world. Why? 1/3 of all women and half of all men are going to be diagnosed with cancer, right? Early detection and treatment is the way to solve cancer in most cases, and if it's customized to that individual, it makes a profound difference in its effectiveness, and that's where we can make a difference. Using high-performance computers, the Knight Center for Cancer Research at the Oregon Health Sciences University is working on analyzing human genomic profiles and creating searchable DNA, customized DNA maps. And what I'd like to do is share directly from them with you what they're doing.
If you trace the origins of personalized care, my view is that it actually comes back to the drug we developed here, which was Gleevec. And what we defined was that if you understood what drives the growth of a cancer, you could attack that specifically, and that's the promise of personalized medicine, taking each individual patient, attacking the cancer at its roots, and getting high response rates with good durability and minimal toxicity. That's a completely different paradigm from what we do now, which is just to kill cancer cells because they grow and divide. When we think about delivering personalized cancer care, we have to start with collecting an enormous amount of data. So right now, we've sequenced a couple thousand cancer genomes. We need to take that up to 1 million or more cancer genomes. But when you start to think about 1 million cancer genomes, the amount of data we're going to collect and have to sort through is actually mind-boggling. We really need enormous compute power to really discern what is going on in cancer. One of the things I've said for many, many years, you can't tell a patient to be patient. They need treatments today.
The collaboration with Intel will develop computer architectures that are optimally suited for the business of precision medicine. One of the things that we have to do is generate the DNA sequence of an individual cancer and to put all of that information together in a timely manner to be used to manage the patient care. Today, this takes days computationally. What we need to do is to move that down so that the information can be generated only in an hour or two. What we have from the Intel side are world experts in how it is that one develops advanced computer technologies, so it's been a great exercise in multidisciplinary collaboration.
What excites me most about the future is the fact that we're making an impact on cancer like we never thought we could do. I want a future where I can look every patient in the eye and say, we have a treatment We know it's going to work, and your cancer is not going to be a death sentence.
Pretty good. So as Dr. Drucker said, in this next era, we're moving a biology problem to a computational problem in the treatment of cancer. Computing doesn't get any more personal than when it saves your life. So I'd like to share another story with you, and it's a story about an Intel employee. In fact, one of our fellows who's here with us at IDF, he fought a 24-year battle with cancer. When he was a young man in college, he was diagnosed with kidney cancer, and he was given a few years to live. And he went through dozens and dozens of debilitating cancer therapies, and he was very brave, and he defied all of his doctor's odds for his longevity. But in the end, the cancer never went away, and his kidneys did eventually fail. Recently, in his work that he's been doing, he was visiting a genomic company, and they asked if they could sequence his tumor. And he said yes. He allowed them to do it. And what they did is they shared that data with all of his doctors. I'm not going to tell you the end of the story. I would like you to help me welcome Intel fellow Eric Dishman to tell his story. Alive and well.
Thank you. Alive and well. I think I've had more predictions of my death than maybe even Moore's Law.
Moore's Law is alive and well, and so is Eric. All right, Eric, why don't you tell everybody what happened the day that you showed up at your doctor's and they had your tumor sequence?
It was just miraculous. At that point, I was so sick, I was going to the doctor like twice a week. So it was my Thursday appointment, and I walk in, and they've got some of my East Coast physicians on Skype and some doctors on the phone, and all of my doctors in Oregon together, and I'm like, uh-oh. And then, they basically tell me that 90% of the drugs that they had put me on were never going to work because this genomic map had revealed this to them. And they basically admitted that they had mischaracterized and sort of misunderstood my cancer for over 2 decades.
And then what happened?
Well, at that point, then they had the good news, which was, we think we understand enough about your cancer, and it's really Eric's cancer. It's unique, like the physician said. Mm-hmm. We're going to put you on this drug for completely different organs and see how it goes. 4 months later, I walk in for my diagnostics. The technician's kind of looking in shock at the scans. They do them again, and they're like, you're cancer-free. You can start the whole kidney transplant process at this point. So,
congratulations. Amazing, right? So. Now that is miraculous. And I want you to share with the audience how now your work at Intel is about scaling that out so that other people can have this experience.
Yeah, it's exactly true. I mean, scale is the thing, and this is one of the reasons I work at Intel. Probably less than 50,000 people on the planet have had access to the kind of whole genome sequencing that I've had. And that's generated about 2.5 petabytes of data. If we had every cancer patient today having a whole genome sequence like once every 2 weeks, which is what they would ultimately want to do, it would generate 500 exabytes of data. And that's just in the US. So as we think about this globally, how do we scale? So we've got our product teams in there working on the fabric, the storage, the compute. I mean, the whole system, how is it possibly going to be done? On the policy side, we're working on how do we deal with the privacy and the security and the ethical issues of sort of scaling this. On the R&D side, it's everything like you showed, from biochips to big data and solving breakthroughs there. And then finally, on the sort of human and sort of education side, we got to figure out how we're going to create a genome-ready workforce, train 1 million doctors on how to incorporate this data, and move forward on getting biologists to understand programming and programmers to understand biology.
Well, thank you for sharing your very personal story with the audience, and congratulations on being cancer-free.
Thank you.
Thank you. So 20 years of ineffective therapies and the expense and certainly the worry of what Eric went through, all of that changed by the benefits of personalized medicine and cost-effective integrated computing. Affordable genomics, cities that reroute traffic and alert you to problems. A few years ago, a lot of what I talked about seemed like science fiction. And today, you can see it's in our near future.